lecturer in combustion and fire dynamics at the University of Edinburgh. And you're going to be talking a little bit about some underlying modeling inputs to, for example, CFD modeling. So, the stage is yours.
Okay, thank you. So I'm not talking about CFD modeling. I'm aware that the session in the room next door is actually focusing on modeling. I'm talking about the science that underlies the models. And this is work done, I noticed in the program it just credits me, but I really must credit my co-authors, Emma and Katja, who did all the work. They did this as part of their final year student project last year in the University of Edinburgh. We are one of the few universities that has an undergraduate degree program in fire safety engineering, or structural and fire safety engineering. And the topic of this really came out of a conversation I had with Hauke Ingesson from SP. We actually co-wrote a chapter for the forthcoming new SFPE handbook that was mentioned earlier. And during the process of conversations regarding that, we were talking about combustion in tunnels and how much of the air that goes down a tunnel actually can get consumed during a fire. And we had some interesting conversations, and we talked about the conventional mixture fraction combustion model. I didn't necessarily use those words at the time, but it comes down to a discussion of flammability limits and when a flammable gas-air mixture will actually burn. And so, to give you an overview of what I'm going to be talking about for the next 10 or 15 minutes, basically the context is that modern fire safety engineering relies to some degree on predictions made by computer fire models. FDS is the one that we're all most familiar with. It's the most widely used. Please do not take anything I say here as a criticism of FDS, because it is a great tool, provided you understand its limitations, and it's one of those limitations that I'd like to address. FDS calculations of heat release, which we care about, species production, which increasingly in a performance-based environment we're questioning, what are the tenability limits. Species production in the model is important, and both of those calculations are actually based on a very simple, some might even say simplistic, mixture fraction combustion model. And I'll be presenting some experiments which basically shows combustion behavior that is not consistent with the mixture fraction model that's built into FDS and other models. And I mention FDS only because it's very popular, but it is by no means the only place that this model pops up. And like all good researchers, my final conclusion will be that we need to do more research. We need to actually understand combustion at the limits of flammability more than we currently do, so that those advances in understanding can actually go into the next generation of computer fire models. So, to talk about the mixture fraction model, what do I mean about the mixture fraction model? The best way of explaining it is this graph from the FDS version 5 technical reference guide. This graph does not appear in the version 6 technical reference guide, although I believe more or less the same mixture fraction model is used, which is why I have to use the old version. Essentially, FDS calculates the mixing of air and fuel produced by the fire, and within each cell in the domain, it needs to make a decision. Can this cell allow combustion or can it not? And essentially FDS and other models make that decision on the basis of this graph. If there is less than, well, at 0 degrees centigrade, if there's less than 15% oxygen, combustion does not occur. Even if there's a flammable gas there, if there's only 10% oxygen in this cell, FDS says no combustion. As the temperature goes up, obviously the chemistry can change, the dynamics change a bit, the percentage level drops down. so that, for example, at 800 degrees, we could have combustion of a 10% mixture. We don't have at 200 degrees, 10% oxygen in the domain of the cell of interest. And according to the simple model, as we go to just above 1400 degrees centigrade, basically that's the point at which, if there was flammable gas and any amount of oxygen, it would combust. The oxygen would get used up, and essentially it's at that point that we could consume all the oxygen in a cell. The implications of that, I've just drawn a dotted line on the graph here, are, say, the temperature in our cell of interest or in a volume of interest does not exceed 1100 degrees at any point. Then, on the basis of this mixture fraction model, we would assume that combustion would occur down to the point of about 4% oxygen remaining, and at that point, combustion would stop. And we would expect to see 4% of oxygen left in the exhaust gases, according to this simple model. And as I say, this is the simple model that's built into the majority of our CFD fire codes. So that's the background. That's in some ways the state of the art. As I say, it is a simple model, but it's a simple model that's widely used, whether you realise it or not. So, as I said, this came from conversations with Hauke Ingerson. He told me about some tunnel experiments, model scale tunnel experiments he'd done, where they'd observed 0% oxygen in the outflow, and yet the maximum temperature they'd recorded was nowhere near 1400 degrees. And I said, why haven't you published this? And he kind of shrugged and said something, you might get there eventually. I'll see if I can publish something first. So I set a couple of my students working on this. They did a series of fairly simple experiments in, I hesitate to call it a tunnel because the cross-section was only about that size. It was a duct containing a wooden crib. It had a fan on the end blowing air into one end of the tunnel. We had a chimney at the far end of the tunnel duct. And we decided that we would analyse the gases flowing up the chimney because they're well mixed and you don't get any stratification effects once you're in the chimney. It should all be well mixed together. So if we record an oxygen concentration in the ducts, that should give an idea of the average oxygen concentration that's been flowing downstream of the fire location. You can also see in the image there 2 thermocouple trees. I think we had 8 measurement points or maybe it was only 6 on each tree. One just behind the fire, one further down the tunnel. We made sure that there was sufficient flow of oxygen that all the combustion gases and all the products of combustion were going along the duct and flowing up the chimney. We carried out 11 tests with wooden cribs, as shown in the picture there, either 4 or 5. I think that's a pile of 4 that you can see there. Recording the oxygen concentration and the outflow and the temperatures. You can see from the graph there, this is from test 6, that the temperatures were peaking around about 1100 is the highest. Some temperatures elsewhere in the duct were a bit lower. Certainly nothing in the region of 1400 degrees centigrade. So across the 11 tests that we did, the maximum recorded temperature in any of those tests was in test 8, and it was 1235 at one point in space. Oddly enough, if we take the column on the left there, it shows the maximum recorded temperature at any point in a test, and then the column on the right shows the average temperature across all of the thermocouples. So we're looking at the average, because obviously we're considering the average flow out. We need to know what the average conditions are in there. And oddly enough, the temperature, the test with the highest temperature was also the test with one of the lowest averages, for reasons that are still not clear to me. But as you can see, the average temperature varied between about 950 through to about 1091, I think, in test. Yeah, 1091 in test 2 was the highest average temperature. So on the basis of this, we would expect that the outflow gases from these tests should always contain a small percentage, 2, 3, maybe 4% of oxygen coming out. By the way, I should say in the picture that I'm showing you at the side of the screen, the flames at the top of the duct do not mean that the flames have been the whole way along inside the apparatus. That's just demonstration of the fact that there are unburned flammable gases coming out, meeting fresh oxygen and burning at that point. There was actually no flame inside the chimney. It burned out somewhere inside the duct. Unburned gases went up the chimney, and then when they encountered fresh air at the top, that's when they reignited. So let's have a look at test 6. The oxygen concentration in the outflow, you can see there fairly clearly in the blue graph, drops to 0. According to the mixture fraction model built into all of our codes, our CFE models, it should have been about 2.5–3%. We should have expected to see 2.5–3% oxygen in the outflow. We didn't. It wasn't just that one test, of course. As I said, we did 11 tests. You may see, I'm not sure if all the dots are in the graph. Some of them, sure enough, we see significant percentages of oxygen. But there's enough points on this 4 points as shown on this graph here on the x-axis, basically at 0% oxygen at temperatures way below 1400 degrees. And that's as far as we've got in this research so far. One of the joys of working with master's students is they do a lot of work in a short period of time, but then they leave and they can't carry on the work. So the work needs to carry on. We need to actually understand what's going on here. Why, in one test there, at a little over 1,000 degrees, are we seeing combustion of all of the oxygen in that apparatus? We don't know. But surely if our models are to represent reality, then this sort of behaviour needs to be picked up by future generations of models. That's all I really want to say. My conclusions are what I've said. In some tests, and I admit that this is ventilated tests, we're blowing air down, and maybe that makes a difference that we're blowing along the duct. Zero oxygen conditions were repeatedly observed in tests where the maximum recorded temperature did not exceed 1100 degrees or very slightly over that. The current mixture fraction combustion model that's used by the majority of CFE and other codes out there says that should not happen until you get to about 1400 degrees. So we've got about a 300 degrees uncertainty here, and that's quite a wide band. FES cannot predict this behaviour because it uses the simple model. And so the good academics' conclusion in every talk is we need to do more research. I think in this case I have justification in saying that. We need to do more research, we need to do more fundamental research, not using the model but actually doing real experiments to investigate flammability limits at high temperatures, to investigate the way that, maybe it's a question of the way that mixtures burn in forced ventilation conditions. That might be the case, although conversations I've had with some of my colleagues that have done compartment fires, again, they've seen compartment fire tests 0% oxygen in the outflow when they didn't have forced ventilation going in and temperatures again about 900, 1000, 1100 degrees. But we need to understand what's going on there. And then, and only then, can we actually put a new model, a new submodel into CFE codes like FTS that actually better models reality. So, thank you for your attention, and I'll happily take any questions.
Thank you very much.